I think it's time to get started for our panel discussion. Let me first introduce our panelists. And Tony Levi is a professor of the ECE department and also the physics and astronomy in the Viterbi School of Engineering. And then Jonathan May is a research associate professor of computer science, Viterbi School of Engineering. He's also a research team leader in the Information Science Institute, also and the Viterbi School of Engineering. Then Peter Beerel, he's a professor of ECE department in the Viterbi School of Engineering. And then Ajey Jacob, he's the director of advanced electronics in the Information Science Institute, ISI, and the Viterbi School of Engineering. So I have a few questions, and I think we can start with the question list. And then for each question, we would like to get the opinion of our panelists. Okay, so the first question is shown here. Basically, I like our panelists to talk about the potentials of edge AI. That's kind of an easy question. And you know the applications and the potentials of edge AI, and also what advance in the last 3 to 5 years are enabling new innovations in this area. I guess who want to go first? It's easier to go first. Then yeah, Tony, you are.
I can say some things. I have a slightly different approach, but the potential of edge AI, it's difficult to discuss things that are not extremely well defined. So I'm sure that everyone who has attended this symposium, has a sense of the diverse range of activity in the field, and it's great to see that. There are interesting problems bringing machine learning to the edge, and I was, the advances in an inspiration from biological systems and their understanding of that is also sort of indicative of what might be in the future. Murali Anavaram, gave a fabulous presentation on the on privacy and information leakage, which is also going to be almost certainly in our future, trying to make systems that actually have privacy built in. There's an outstanding issue from my perspective. If you look at the presentations and you ask where are there gaps in what is being discussed, and where are there gaps in the community and in understanding? One thing that concerns me is, understanding fundamentals. And what do I mean by that? For example, what is a measure of intelligence? If you intend to do science, then there should be a measure by which you quantify an objective and the distance from that objective. I haven't seen anything in the last 2 days on that topic. And there are other things to do with technology and where things might be going. There should be a recognition that man-made microelectronics is fundamentally different from biology. Biology is driven by survival, operates close to equilibrium, and is purely classical. Microelectronics, contemporary microelectronics with 300 transistors per square micron can operate far from equilibrium, offers the potential of extraordinary precision in calculation, something biology can't do, and the possibility of non-classical resources such as quantum entanglement, all of which can boost sensitivity and processing at the edge. So that's sort of, my sort of perspective, and perhaps addressing a little bit of your topic for discussion. On this, there are other things that could be said, but maybe I'll wait for others to sort of respond.
Yeah, those are excellent points, Tony. Yeah, so by the way, audience, if anyone have anything want to chime in, even though we have limited time, but you're welcome to, offer your opinion either with the panelist or against the panelist. You're all welcome. Yeah. So yeah, who else want to talk about it?
I can chime in, I guess.
Yeah,
So looking at what we heard today, I find it amazing that we have a lot of new work in the devices level. And we're not just talking about memristors, but also on those oscillatory circuits. So as Moore's law seems to be tapering off, as we look to next generation devices, next generation materials, it's really amazing to me to see we have to make a fundamental shift. Maybe we need to be thinking about oscillations and how that will represent data from sensors. And then the question will be, well, how do we extract the information out of that efficiently and do the appropriate machine learning? It's going to change at least the first few layers of a machine learning network. And so I think that what I'm seeing is that as Moore's law is going to an end, there's a lot of interest and a lot of breakthroughs in the devices. And where we're headed is that really cool co-design of what machine learning algorithms will look like that can feed off of these new devices, and they force us to think in new ways. I'm kind of excited about that.
Yeah. This is the prime time for rethink the architecture of computing. And yeah, so thanks, Peter.
So I will not touch upon the intelligence that Tony has brought in, because it's a big discussions that we should have on it.
Mm-hmm.
But about what Peter said, Peter said about the future devices that is required, future devices that we are seeing today that could be that could be of potential use. The question that is asked, okay, potential of edge AI, and I understand that there are a plethora of edge AI devices that are already there at our houses, in terms of all these Amazon AI devices or some other AI devices at the home, IoT devices at the home. But then how did this all, how are all these things getting implemented? It's primarily because of the extensive improvements that has happened in the high performance computing. The technology has scaled. The technology has scaled all the way down to 5 nanometers, and we have silicon out there that can actually do a lot of fast processing. 20 years ago, when I heard a talk from NTT in Japan, they were even doubting if there would be any speech recognitions hardware, that if there would be a hardware that can actually help do the speech recognition. Today, all these things are available because of the high performance computing paradigms that we have developed.
If I could just add on, I think that the PyTorch frameworks, the TensorFlow frameworks, and then going beyond that to the HLS frameworks that allow us to put them on FPGAs, it's more than just the raw computing power, but the frameworks that people have developed, as well as just the whole paradigm of open source, where now it is just by default, you write a paper, you need to open source your code that other people can then feed off of, has accelerated this whole area crazy compared to EDA and CAD in the past, where we'd have a conference, we'd be happy to have 1,000 papers submitted into the top EDA conferences. Now there's 10,000 papers per conference in ML. It's crazy fast, and it is that whole framework of rethinking about open source and even open review process is accelerating the research in this area quite well.
I want to jump in when you said that, Peter, to throw some cold water on that. Coming from the world of natural language processing, I would say I'm probably the most outsider here on this panelist. In fact, I generally do not operate on the edge. Everything we do is, I don't know, whatever the opposite of the edge is, in the gully. So when we get to the challenges, I want to just put a pin in what you said, because we're all in the NLP space a little bit bamboozled by, say, GPT-4, which was released this week with the very provocative saying the quiet part loud that no, we're not going to tell you anything about our model, and in fact then doubling down, saying no, we were wrong, we shouldn't be open, in fact, and what the challenges that could presage are, especially when we're getting to issues where edge enabled devices are going to be so critical in terms of multimodal embodied data gathering. But the question was about advances. And so from my non-edgy perspective, I kind of have to generalize and say, well, being able to do things with less data, right? So things more quickly where there is less communication, say, needed, is an important advancement. And to that end, I would say, getting back to the GPT whatnots, that this notion that what we're now calling in-context learning, but essentially, a few shot prompt within at inference time, so the model doesn't need to be adapted, where you have a model that has fairly generic capabilities, is quite exciting, because then you don't have the need to, for example, retrain to fit a domain in the field, and there's great potential there. Although again, that will get I want to put a pin on that for going into challenges, because I think when trying to use that kind of model in the edge environment, we're going to have very, very difficult time. But I think that's an exciting challenge to get to if we can have a model to try to adapt.
So Jonathan, because you have been working mainly with the cloud rather than the edge, that's one of the reasons we have you here, to have the opinion cover the whole spectrum. So you mentioned one of the very interesting point for the GPT-4, they tend to be more closed rather than open. You think that what's the reason? It's a commercial reason, or safety reason, defense safety reason?
They said the quiet part loud, right? I mean, the paragraph, it's what, on the first or second page of the GPT-4 paper, which we should be so thankful they released a paper. ChatGPT had no paper with it, right? Let me see if I have this there. The quote was something along the lines of, I'm not going to be able to find it fast enough. But basically, it's for strategic purposes and then also for privacy was kind of tacked in on there. But I think the real issue, and like I said, so Ilya Sutskever, who's the co-CEO, co-founder of OpenAI, said, no, there's a lot of money to be made here, right? There's a lot of companies. I'm paraphrasing, but basically, like, why would we give it away, right? So we're not going to tell you how many parameters are in our model. We're not going to tell you what data our model has been trained on. We're not going to tell you, potentially they're using the data in ways that it shouldn't be used, right? But they're not telling. I don't know. We're not going to tell you anything. So you're on your own, kid. So I can imagine, right? Like doubling down on that, right? Like maybe people follow that lead. Certainly, they're more than willing to use the technologies that were created in this era of open sourceness and sharing, right? Things like PyTorch, right? And I mean, heck, the transformer itself, right? Which presumably GPT-4 is based on, but we don't know. If that happens, if you have this one-way direction, right? Like, what shouldn't another company that's doing a lot of research say, okay, well, we're also not going to share what we do. In fact, that is true. Google recently released a paper about an embodied multimodal system, and that model is completely not open. The data is completely not open. And then, well, so is that going to filter down to academia? We actually we're not going to have access to this model. We're not going to have access to this data. Can we build upon it? We can create our own thing. Should we release our own thing if a company is going to snap it up? I don't know. I think it's really a significant societal challenge.
Right. So there's a lot of activity, there's a lot of chaos, there's a lot of swarming, and what the community can do is try to apply some sort of reasoned thinking to how to plot a path forward and try and understand what they're working with. So let's start off with materials. What can materials and devices do? We don't have an automated, this is something that could be done. We don't have an automated systematic search for the specification, discovery of materials, geometries, and models and modules that perform, extreme levels of swap, precision, and adaptability at the physical layer, the physical level. That's something as a community we ought to recognize and do something about. Then there are, the issue that's come up multiple times during this symposium is there's much talk about agile hardware and software and co-design. We ought to establish what this actually means in practice in terms of numbers. So, for example, as a community, we might decide that we can make a great deal of progress with, let's say, 1 week turnaround for hardware implementation and a 4-week turnaround for system level demonstration, corresponding to a 4-week sort of gestation period for an iteration of a edge capable component. And then, of course, there are the applications. What are we striving for? Are we striving for predictive capabilities, such as a sort of weather forecast for the smart city, meaning what's going to happen in the smart city a few days from now? The edge will be an important part of that. And forecast of society in general. An obvious first step for the edge is sort of personalized predictive healthcare and so on, which edge will play an important role on. So there's lots and lots of challenges. And I think as a community, maybe coming out of USC, there's a need for a systematic approach and sort of understanding of fundamentals, which I mentioned earlier, and the development of sort of guardrails and roadmaps. The most efficient progress will be made if there are clear objectives and a coherent set of approaches to get there. So I don't, worrying about whether it's open source or not is a distraction compared to laying down a sort of path forward for the whole community. What's happening today and the excitement of today and the swarming of individuals, 60,000 citations on a paper or whatever in a few weeks is something perhaps to make note of, but not to be distracted by. Much more important to look further in the future and have a sort of reasoned thinking about how you're going to get from point A to point B in a reasonably efficient way. It addresses all sorts of things, including, how you're going to improve energy efficiency, which was mentioned a number of times in the last few talks.
Yeah, I think we already touching this the second topic, which is the challenge and potential solutions, especially for edge AI. So sorry, Ajey, go ahead.
Oh, no, I mean, the challenges, as was discussed earlier, bandwidth is a challenge, especially when it comes to distributed ecosystem, how to tackle all those bandwidths into one stream. Stream it, data storage, and then the past developments with respect to, it was also discussed on the cloud basis, but the server development, the switches that is required for the server, all the circuits that is needed to maintain the servers or to have the servers consume all this data, to seamlessly transfer all this data. All those things all those things are a challenge, and there are probably potential solutions out there that Tony was trying to allude with respect to materials. There are some optical solutions that people are trying to come up with to address all these things, especially with respect to transferring the data. But one primary challenge that I think is there for the edge AI is with respect to the algorithm, and that is with respect to the accuracy. And all the other item was probably touched briefly, but that is with respect to the security. So these are the two primary challenges that I think has to be addressed both from the hardware point of view as well as from the software. But accuracy has to be dealt with. Accuracy has to be dealt in by building new models, maybe new algorithms, maybe.
You say accuracy
Accuracy, yeah.
for
Because we did some work. I mean, Peter can explain on this. We did some work and we tried to get only certain percentage of accuracy, and it was limited by the availability of the algorithm, the model that is available there.
So I guess if depending on what kind of accuracy you are talking about for the
so inference accuracy, you're trying to do object detection and tracking for something as complicated as autonomous driving. Tesla can tell you this is a hard problem to get close to 100% accurate, right? And no matter all of the models that people have explored, all of the GPU hours that Tesla and others have put on it, it is still not perfect or even close to perfect. And this will remain a challenge as we try to apply these kinds of systems to safety critical things like autonomous driving.
Yeah, but Peter, your driving is not perfect either, but it's good enough.
But there's
But
a
it's good enough.
There's a difference.
So this is the risk
failure and robot failure.
Right, there's a huge risk because robot failure would be all Teslas at one update could fail, and that would be catastrophic. Whereas we, as human failures, it's more a one-off. So there's still a risk.
I mean, there is also like empirical studies on the way humans are messing up versus the way AI is messing up, for lack of a better term. Even in there was a talk earlier this week about this in the NLP space, where overall, yes, the model is better, but the failures themselves are spectacular, and it's the spectacular failures where people pay attention. As an example, would you want, like, if you go in and go and get surgery right now, I just found a little evidence, I don't know how up to date it is, there's like a 1 out of 31 chance that a surgeon will make a mistake that's going to lead to an infection. Not necessarily a damaging infection, but something that might lead to extra, or not a deadly infection, but something that might lead to extra time in the hospital. It's reasonably common, right? But if you had a robot surgeon who would never forget to wash its hands, right? But might, like, 1 out of, I don't know, let's say 1 million times, think that your open chest cavity is a sink and attempt to wash its hands in there, and even be restrained by nurses ahead of time. If that should happen, right, 1 out of 1 million times, I think I would prefer the 1 out of 31 chance, even though it's empirically a greater risk of inconvenience to me. And I think that that's, the societal reality, which is not necessarily a rational reality, should be taken into account.
I going back to this challenges of edge AI and what Ajey said, this is also related. There are so many edge devices that distributing these extremely complicated models across a family of devices, or the devices in your family, has tremendous applications for a variety of things. We heard about federated ML. That's just one model where you have one central server and a bunch of clients. We heard of pipe edge and quant edge, where you have maybe a linear chain of these different ones where each node takes maybe a few layers of a model, but there may be many more. How to take advantage of these things and still do it in a secure manner, because maybe you don't trust one of those devices if you're doing this in a military setting, or you want privacy in the communication between the devices. How do you do that? I think becomes really interesting. And then I'll just say that's true for both what we do right now. A lot of is inference on the edge, but as we try to do personalized stuff and we want to do training, and the problems get even harder and more interesting.
I wanted to ask about the materials point that Tony brought up, because I really know nothing about this except for the layperson's reading of occasional articles that talk about the rare earth material that's needed to create all of our sophisticated technology. And I wonder, I mean, that seems very, it's difficult to extract, and it causes lots of, environmental impacts, and possibly more importantly, in terms of getting, in terms of the availability, you have, socio-political issues that can quickly cut off supply. I wonder, is there work in this direction to avoid this kind of material, or to be able to reuse what we have, or is this just inevitable and there's nothing we can do about it?
Well, the word rare in rare earths does not mean that it's rare.
Right. But it still is difficult to extract.
The way to hedge against geopolitical events, of course, is just in the same way that the way to hedge against geopolitical events in fabrication of CMOS circuitry is to diversify the geographical location. And that's something that can be done and will be done, perhaps driven by politics, but definitely eventually driven by financial concerns. So on the materials side, what I was alluding to is not extraction of materials from the earth, and it was the systematic search for material function that has not taken place, that ought to take place. What has been going on is sort of ad hoc, Edisonian. We get this to work based on what I knew before. I'm using a bit of hafnium or something oxide because that's what I think I ought to do next. A machine hasn't searched. A human has sort of pedestrian sort of approach has been going on. It's extremely inefficient, literally an Edisonian approach. And we have an opportunity with compute power that 30 years ago was not available and is available now. We have the tools, meaning the software, to do such an exploration. We're just not doing it. So there's a major challenge in just finding material function. I got plenty of examples I could bother you with, but we don't have time for all of that. There's also the specification. What specification do you want? And people sort of in an ad hoc way write down something and they literally don't know what they're specifying. They don't know the consequences. And so a machine can do a far better job if only you could train it up to do that exploration of what the proper specification is for a system. And of course, this plays on co-design, which ought to be much more dynamic than it is at the moment. Again, co-design as implemented today is also ad hoc and sort of Edisonian in its approach. What do I know? Scratch my head anyway, I won't characterize it, and come up with something that may or may not work. So lots and lots of ways to bootstrap and use modern techniques, whereas 30 years ago, this was not possible.
It seems like the way for that has been paved well, at least in terms of the material interaction proposals by what's been done in like protein interaction, where there have been models that look at the biological research literature and databases of known interactions between molecules and attempt to predict what experiment should be tried. And even there have been cases where that's been connected to an actual wet lab with robotics. And I wonder if the analogy would hold.
Not in traditional inorganic semiconductor world, microelectronics world. There is a much more general sort of issue that comes up, which is partly materials, but also covers the full stack, as what people would describe it, is the sort of human-machine interaction and what it means. That's another thing that ought to be looked at more than it has been. But that's a separate topic entirely.
I want to touch upon the accuracy part and also bring in the co-design. And accuracy is a relative number that was actually discussed earlier here, but we can only through experimental facts that we can make it make something accurate, very accurate. And that essentially means that one got to have the algorithm hardware co-designed to make sure that the algorithm, when implemented onto the hardware, is giving you the accurate value. So there has to be, for the edge intelligence, there has to be this marriage to happen.
So this accuracy usually is not emphasized on the edge. But yeah, so, you know, I mean, Peter, you know, when we talk about the training in the cloud, the accuracy is emphasized more. So edge, like Tony pointed out, you know, we do not need 100%. The people are not 100% accurate, but yeah, I see the point, right? So if you make one mistake, it get copied to millions, you know, of those devices, that will be very dangerous. But on the other hand, yes.
I was going to say, there's another aspect here. It's just that we need accurate models of the new devices at a level of abstraction that we can then do something with it. So specifically, every new device you guys come up with, memristors, oscillations, they may be subject to noise, and there's some nonlinearity in it. And if we and there's programmability so that we could program it as if it were the first few layers of a machine learning algorithm. So we want to build a model of that into our PyTorch frameworks.
Right.
And that model may not be accurate, and then we got a problem, right? If that model doesn't accurately represent the hardware, if it doesn't capture all the nonlinearities, the sensitivities to noise, the process variations, then we might think we have a great solution full stack, but because our models are not accurate, we still have work to be done.
Totally agree. So that's a kind of a different accuracy we're talking about here. So yeah, definitely, because it's a new device, of course, the model needed to be, you know, optimized and become more and more accurate over time. Not to the transistor level modeling, of course, over many years of development. And the devices are changing because it's new, then your model has to change as well. But for the AI accuracy, you know, that's the inference accuracy. Then the bad thing is once you make a mistake in there, it's get copied and distributed millions of copies. Everybody make mistake. But on the other hand, it's easy to detect. Once there is a mistake, then you know, then you go to fix it, then everybody get fixed. So the question is, you know, I don't know, probably everybody have heard Jeff Hinton recently proposed something called mort computing. And so basically he was saying, you know, even though the hardware we are using is not going to be exactly like what we have now, it's an identical copy. You know, the CMOS foundry tried very hard to make the device very accurate. Everything is identical. And then you distribute all of them, then everything is exactly the same. And they spend a lot of money, energy, actually trying to make it identical, right? That's in the past. But he's saying now, can we grow hardware in a way, you know, like people grow, they grow slightly different way, but adapt to the environment. And that's kind of an edge. AI, you know, the hardware algorithm, they're same thing. Their algorithm just work with their hardware. If the hardware dies, the algorithm, they cannot be separated. So that's
a great idea.
He proposed.
It's essentially fine-tuning your weights to the hardware itself. And you can do that fine-tuning at the edge with edge hardware. And that's a wonderful idea that could make the design, particularly of the analog hardware, much easier. We don't need 12 bits of accuracy because we'll adapt to whatever you have, would be, you know, the argument. And it doesn't need to be the same for every chip if we can adapt our models for every chip, for every person. But that will take an effort, and it'll take time energy to train for each individual phone, for each individual IoT device. But a really exciting dimension, I'd say.
Absolutely, and you know, just like we age, and we have to change what we do, let's say how we drive, Peter, with time. So the edge device also needs to adapt over time, both in the software piece, the algorithm piece, and the hardware. So that is, in fact, the optimal approach to dealing with edge components.
Another, probably one major challenge that I think is collecting the data, because we have several sensors, and these sensors would be collecting similar information differently, and then doing that processing, and then it could be doing processing on itself. The machine that collects the data could be doing processing on itself, which essentially means that you're altering the raw data. And then if you're implementing your algorithm onto the into the data that is already processed, you may not get the right inference that you want to obtain. So I guess those are some challenges that devices at the edge requires to tackle.
Mhm. So what are the potential?
There was a question from Yolanda, Joshua, in the
No, okay. Yeah. So yeah, question from Yolanda for the panel. Many AI researchers are generally not very aware of edge computing advance, such as the work presented at this symposium. What strategies could we pursue to connect more deeply the research on AI and the intelligent capabilities and the integrated applications with all these exciting advances on edge device and architecture?
Well, Yolanda, you started this with a nice symposium. I think the dimension that might be missing is the pull from industry. What are the pain points that they see? They tend to have a better sense of what next generation applications would be really good if they could only do this. And having these kinds of symposium where we also invite our industry sponsors and maybe government as well to highlight some of the challenges, we could maybe create more of a almost like a full stack view of the problem.
I don't know if I'm allowed to share the screen.
Oh, yes, you can. Yeah.
I'll have a
fine.
bash at sort of addressing what Peter and perhaps Yolanda, what Peter was mentioning, and that is what industry, what's on industry's mind. On industry's mind are not the things that typically drive academic research. What's on industry's mind looks like this. So you see global markets, and these are some predictions in 2023 and revenue in 2030. They're all from the same source, so presumably consistent. Compound annual growth rate, you see 5G, global AI, global IT, and global cloud computing. Industry wants to be where there's money to be made with high compound annual growth rate. They share a totally different set of objectives compared to the types of things that we have been discussing and the way in which we approach those things.
I'll just say we had some nice talks with, I think it was in the Meta, or it was in the Amazon Center, where we had some folks from Alexa saying, here's a little bit of their roadmap. Here's what the latest new things they're doing for Alexa. And then we could have a little bit of a conversation of what are the next few things that they wish to do, and how that, frames the idea of bringing in an Alexa with a screen and a camera that can track where you are moving in the room, if you so choose to enable that feature, and have the NLP communication with Alexa better, and have this sort of multimodal aspects, I think puts into focus examples of where people are going on the edge. And that's just one example. I think making sure that the researchers all the way down from the devices to the people who are doing the co-design to the algorithms have a sense of these range of applications is always good.
Yeah, I think, from the government, especially they are aware of the importance of co-design, and they have a few programs issued, it's just emphasize on the co-design. Even NSF, now a lot of, program, they need the multidisciplinary expertise get together to respond to the proposal call and DOE. And so just in April, there will be another workshop in Sandia. Actually, it's sponsored by DOE. The name is co-design. So yeah, definitely that's because this is a new thing. We needed to know each other's, the algorithm needed to know what's new in the device, and the device needed to know how the algorithm can help us with the new discoveries. So I think it's kind of now we are in the co-design direction. There are activities trying to enhance this, but within our institute, for example, at USC, we have different department, different expertise, and we will have some symposium like this to understand each other, work with each other, and eventually have some center as a platform to support us to do that, right? Yeah.
It's interesting, Joshua, that most of our programs, our educational programs, are siloed. You have a program in analog design, you have a program in digital VLSI, you have a program in machine learning. Many of our programs are too siloed for the next generation challenges. And we need to be thinking that next generation researchers might need to have a little bit more breadth so that they can understand multiple of these issues and be able to address it.
Yeah, that's actually exactly the last topic we're going to discuss today in the next few minutes, actually. So the strengths, opportunity, and the strategies for Edge AI in general, and also for USC. What is our strategy or to advance this? So
we have such strength crossing ISI and ECE and material science and ISE. I think we need to foster that strength and as much as possible fight the silos that we tend to be in. And I think these kinds of symposiums help, and we should do more of them. 10-minute talks gives enough time for people to understand what they're doing. And maybe we just need to figure out how to follow up so that it doesn't just, oh, we did that symposium, but to have more collaborations. I know in just the last few months, I've talked to you in terms of collaboration. I'm now talking to Rayhan to see if there's opportunities to collaborate with Rayhan in the co-design effort. And I've worked closely with Ajey because of previous that, and there are many more opportunities for these kinds of bridging the device, the circuit and the algorithm, and even further the application. And I think we need to do more of that as a group and figure out how to go after large efforts with that vision.
Yeah.
So there is a way to proceed. Years ago, I did a couple of workshops on energy and documented it and whatever. So with the AI at the edge, there could be a USC white paper that basically is a snapshot of where we are now. And there could be a sort of repeat, maybe a workshop in a year's time, and you sort of cycle on that. And I don't believe there are silos. There's just people will walk through barriers if there's enough excitement in a particular area. So you just have to generate that sense of direction, and the rest will follow.
I think that there needs to be more than that. there's parts of these conversations that I'm able to follow along in, but honestly, the vocabulary starts to diverge quite quickly. And I don't even think 10-minute talks are really the right way to communicate this kind of information, and to collaborate on a white paper is perhaps a little premature. If I were to like start adding to a page, I think very quickly we would realize we have just completely different vocabularies and possibly are even talking about related things. But to actually have an active discussion, something like this, but possibly without broadcasting it to the world, so we can feel a little bit more free to make mistakes and struggle to understand very some key concept that maybe takes a half an hour, but like is a real blocker to moving forward, is a way to get engaged, and for students who are really often the drivers of the research to do the same, to be talking one-on-one. Trying to, speaking, maybe a grad student talking to another grad student across departments about a poster, and really trying to come away with a full understanding of that is where you're going to get inspired to, hey, this is really fascinating. I mean, even today, like, Tony talking about the material fabrication aspect of things, this is a thing I didn't know anything about before you mentioned it, right? And I think if you had talked about it in a 10-minute talk, I might have caught it, I might not have. You're probably going to talk about your own work and the things you did and the paper that you published, et cetera. But it's this kind of talk, I think, where the bridging is going to happen, and even more so if it can be done with a one-on-one instead of a 5-on, a 5-on-5 with however many people are watching. So I would advocate more in-person, coffee breaks, basically.
Well, on the co-design, it is indeed true that Sandia is putting a massive effort in that direction. I'm not sure that their version of co-design is the same as ours, but we could organize a sort of get together with Sandia and sort of try and make a partnership. That's another thing, sort of, again, that's sort of more USC centric. And if we're talking to the rest of the world, maybe we shouldn't talk about those sorts of specifics.
I just want to follow up on I think it was discussed, but maybe just as many of these universities have these robotic centers and things like that, exotic places to work. We could probably have an Edge AI center for research, a facility where interdisciplinary or multidisciplinary research is done, where people can come together and also maybe propose ideas that requires to be co-generated, that requires implementation to be co-implemented.
Yeah, that's an interesting idea, AI center. So yeah, because everybody is busy, and we have only 10 minutes for people to just briefly show what they have been working on, and for others to know, okay, I have a colleague working in this direction. If they happen to be interested in that, they can do the follow-up and to understand the details. Otherwise, we cannot have a full 2-day symposium and everybody will get very tired. And we do not expect people will learn every detail in such symposium. Rather, it's kind of you get a rough idea what each other are doing, expertise available near you. So then the key question is how to do the follow-up and the interaction later. And if we can have some sort of platform to facilitate that will be great. We always talk about it to get the student mixed together and they can have some idea interaction. But especially in this topic, we the campus ECE department, computer science, would like to have a very close interaction with ISI, and ISI is not even on the same location. So how to do that? How to get interaction enhanced between ISI and the ECE department is something actually is going to very rewarding, and how to do that is probably a first step. So we are, I think our panel discussion time is up. Anybody have anything needed to say before we close this?
Thank you for arranging such a great session.
Thank you. So now I think we have only so much time for the discussion. Let's continue in the future with other opportunities. And at this, I think it's time to invite Ishwar Puri and our Senior Vice President to give the concluding remarks. Let me stop sharing here.
Thank you. Thank you very much, Joshua, for inviting me. I'm very pleased to be here, and I've been following the previous discussion with great interest. So I think that, it's sometimes nice to sort of stop and think of history, right? There was a famous conference called the Dartmouth Summer Research Project on Artificial Intelligence before I was born, actually, and before many of us were born in 1956. And the whole intent of the Dartmouth Summer Research Project on Artificial Intelligence in 1956 was to have a great collaborative effort where people came from different disciplines, they met each other. And what that conference found was that people never really came together as a group, but they came and went. And so I think, at that time, many people, according to the historians who've written about it, thought that the effort had failed. But that effort didn't fail. People came and went, but they absorbed something. And that started the age of AI. And there was a golden age of AI, from the late 1950s to the mid 1970s. DARPA got involved in AI research and so on. But there were many obstacles, right? Because we didn't really have the hardware during that era to really realize some of these, some of the advances that could happen. Governments got involved. The Japanese government put in a lot of money in the 1980s into developing expert systems. And then AI, of course, got into the popular imagination. And there was two seminal things that happened which caught the imagination of people through the newspaper pages. I mean, the first was that there was a grandmaster that I grew up watching in chess, Garry Kasparov, and IBM's Deep Blue. I think this was in the mid to late 90s. IBM's Deep Blue defeated Garry, and then of course Google had a system that defeated the Go champion, AlphaGo. And so these two were sort of seminal things that caught the imagination of people. And then, of course, we started talking not about AI, but we started talking about big data, data analytics, and then, of course, people started working on natural language processing and so on. And when we think of AI today, it's a fractionated community. Some people think of AI in terms of predictions. Some people think of AI in terms of natural language processing, generative AI. And there are still challenges. So, GPT-4 was released a couple of days ago. And if you look at its performance metrics, it does really well in passing exams that are language-based. But it doesn't do so well in passing exams that are math-based, calculus-based, physics-based. So when we talk about AI and we talk about driverless cars and things like that, I mean, there are several things that are possible, but AI still does not give us a good understanding of the physical world or the natural world. There are other issues also with AI. I think that some of the discussion that I overheard during this this meeting, and Yolanda tells me that 200 odd people have signed up for it and they come and go. And the discussions have been absolutely fascinating, right? On the edge. I mean, I'll throw something out there. What many of the AI agents today tell us about anticipatory events is they tell us about what is probable, but they don't always tell us about what is possible. That is, they don't tell us about that unique black swan event, right? So imagine if we had a surveillance AI agent and it was used, for instance, I mean, I'll conjure up an example off the top of my head. It was used by the intelligence community. It would tell us about probable events, but there was a seminal event that changed things all over the world, and certainly very, very drastically in the United States, and that was 9/11. Could an AI agent sort of tell us about unique black swan events? I think that those are some of the challenges. You know, AI is ubiquitous today. It's ubiquitous in banking. It's ubiquitous in many other applications simply because we are using older algorithms or recently developed algorithms when we are harnessing the power of next generation computer systems. But there are so many challenges. I mean, one of the challenges is understanding the physical world. There's a lot of talk about using AI to develop molecules and materials. Perhaps old style chemistry will be dead, many people say, and the new style chemistry will just be using AI agents. And then again, I mean, the question is, will these AI agents that we use, will they give us the most probable chemistry? Or will they be able to give us the unique chemistry that could really, really solve a problem? I was also at a recent talk by the new director of ARPA-H. And she, of course, was with DARPA, and she brought with her Hallmeyer's Catechism. Hallmeyer's Catechism is a well laid out catechism that guides DARPA in what projects might succeed and when to end them. And she'd added something to Hallmeyer's Catechism that ARPA-H would consider, and that's that's item 11 in her list of what she calls Hallmeyer's principles. And that is anticipating the unintended consequences of ARPA-H technologies or ARPA-H advancements. And so I think that that's another area where we should focus on. What about AI and understanding the physical world? What about AI and understanding unique events as opposed to just the most probable events? And what about AI in terms of understanding or anticipating unintended consequences? So there are many exciting directions where your conversations on AI on the edge can take us. You've discussed over the last 2 days about how privacy is improved if data is processed on the edge, if how emails might be more grammatical when they are processed on your mobile device, and how your bird recognition app would work offline in remote areas. There was talk about technologies using AI in health and medicine, such as sensing through artificial skin, brain-machine interfaces for the stimulation of memory formation, and disentangling brain functions to improve diagnosis and treatment. You also ended by talking about how one must bridge silos. There was some disagreement as to whether silos exist. I would say that silos always exist and they will always exist. And our challenge is breaking them. And the reason silos exist, partly it's because of structure, but partly because even with the lack of structure, when you structure organizations into departments, into schools, into institutes, we segregate culturally and socially into tribes. So when we talk about bridging silos, it's really about bridging tribes. And there was talk also about how different tribes use different language, different etymology, different nomenclature. And it's difficult to sort of, for people in another area sometimes, if not difficult, but challenging for them to understand each other. So I think we have to bridge these tribal divides. I also heard about how, within Viterbi, these divides could be bridged between departments, but there's a whole world out there. And the whole world has bankers, and it has historians, it has creators from the cultural community. So I think, the divides exist tribally, not just within a narrow inside baseball kind of concept, but they exist in the larger world. And that's one of our challenges as well. It's great to see that, this conference, has really helped bridge some of those divides. At USC, certainly our president is very interested in just the sorts of discussions that you're having. And I really look forward to working with Yolanda and all of you to see how I can move the ball on this. Very often people tell me that the university wants this or the university wants that. And I always tell them there is no the university. The university is all of us. All you have to find is a couple of champions, and all they have to do is put their shoulder to the wheel, and this happens or that happens. There are intended consequences and unintended consequences. But there is no central politburo in a university that sits around thinking how I'm going to drive the nature of research in particular, over the next 10 years. Maybe there should be, but I will tell you, this is my 4th university, and I have yet to discover such a politburo or 5 or 10 year planning of that sort. So let's get together and let's work together to move the needle. I will say that as a university, if you want to talk about the university, we're very proud of the role that USC has had in shaping the future of AI. And so I want to thank you for joining us in this USC AI Futures Symposium. And many thanks to, particularly to Yolanda, to ISI, and all of my colleagues from Viterbi. I would like you to be happy simply because my tenure is in Viterbi and I don't want to be rooted out of there. So I will thank you all very much. And it's been great joining you and listening in and overhearing some of these talks. So thank you.
Thank you. So yeah, especially towards the end of the day and the weekend, we lost the majority of our audience, and you still came and share your vision and a lot of interesting insights. That's definitely very helpful. Thank you so much. Yeah. So Yolanda, anything you want to add?
I will say that it's been extremely informative, exciting. I can see so many possibilities in the future. And in the last 10 days, I've had, by coincidence, the chance to talk to people at NVIDIA, Apple, Amazon, which I don't do very often, but I could see all of these discussion in the panel about trying to connect with their vision and the drive that they have to incorporate technology into their systems that includes both the edge side and the AI research side would be extremely exciting. And I really look forward to working with everyone on this. I want to thank Ishwar for making time to be with us, and to all the audience. When we do these symposia, we do them virtually. We have, as Ishwar mentioned, over 200 people registered. And I know from previous symposia that we've done, they come and go and they attend their schedule permitting. And this week is spring break at USC. So I know that there will be a lot of people watching recordings, and I hope we will follow up with more events, poster sessions, and ways to connect better amongst us within USC, and also in the larger world that we just heard is out there, very interested in our technologies. Thank you, Joshua, for co-chairing the symposium with me. It was a pleasure. And thank you to all the speakers for really wonderful presentations. Please come to the website in a few days to see the recordings. And there's several prior symposia in AI topics that we have held that you can also learn from through the website. Thank you, everyone. Have a great rest of your day. Thank you.
Great, thank you. Yeah, have a good weekend.